Y'all, good evening. Tonight we're going to talk about 9.2 tests about a population proportion. So here we're going to talk about tests. When they say tests, they're talking about a hypothesis or a significance test about a population proportion, which again means rho. So let's see what it says here. It says a test statistic measures how far a sample statistic, okay, so that's either an X bar or a P hat, diverges from what we would expect if the null hypothesis HO were true in standardized units. That is, in general, a test statistic can be found by the general equation right here. All right, so this test statistic right here, it's going to depend on one of two things. If it's a proportion, the test statistic would be Z, or if it's a means problem, the test statistic would be a T. Okay, so before we move on to the formula here, let's kind of review what a Z-score was, because that can help you understand this a little bit better. So, when we talked about Z-scores way back a long time ago, all right, if we talked about how far a person, or what a person's Z-score was, okay, it depends where it fell. Okay, so we said before, if this is just someone's value and you just call it X, you would say, okay, I need to go from value X minus where the mean was, right there, and then divide by the standard deviation. So a Z-score is how many standardized units a value is away from the center. Okay, now these standardized units, okay, the standardized units was the number of standard deviations. So for example, in an IQ example, so maybe someone has an IQ of 132 and the mean's 100, and let's say the standard deviation is 16. And to find their Z-score, we would take 132 minus 100 over 16, which would equal 32 over 16, which would equal 2. So this person that scored a 132 actually has a Z-score of 2, which means they're 2 standard deviations above the mean, which is fairly good. Okay. Well, now, instead of having, this was in a population distribution, now let's put it in the context of a sampling distribution. And it's easier to illustrate with means. So if we have a sampling distribution here, okay, each one of these things has like an X bar, and so on and so forth, and right down the center, that's the mu of the X bar. Okay. And it's going to be some value that we get out of HO in a hypothesis test, null hypothesis. So we're going to take a sample. All right, we're going to find the mean, for instance. So to find the standardized score, or the test statistic here, find the test statistic, we would say, okay, where's our mean? Okay. Minus what we think the mean of the population is, so we'll call that mu naught. Okay, so this is some mu naught there, maybe it's 100, or whatever it is, over the sigma of the X bars. So we're saying how many standard deviations is the X bar above or below the hypothetical mean. So it's the same idea. It's exactly the same idea. There's parallels between sampling distributions, test statistics, and just normal old z-scores. Okay, now, in the case of a means problem, this test statistic would be t instead of z, because this has a t distribution instead of a z distribution. So hopefully that made a little bit of sense. So the best way to understand these is to do a few problems. In section 9.2, they just want us to focus on population proportions. Okay, so here's our test statistic. Okay, so let's see what that says. We have our statistic. Since it's a, well, first let's talk about why. If it's a proportion, we're always going to use z with proportions. Okay, so we're going to take our sample statistic, our sample value, minus where we think the true row is, the true center. Okay, so like in our sampling distribution here, that's a normal curve, it's a z curve. Okay, and we think the row is right there. Remember, that's the same thing as saying the mu of the p hats. Okay, so it's some value that we think it is. All right, then we're going to take a sample. So we're going to get a p hat. This is made up of a whole bunch of p hats. We're going to say how many standard deviations is the p hat away from what we think the center is. That's what it does. We're going to take our p hat minus this and divide it by what we think the standard error, essentially, based on this value, where we think what we think the row is. Row naught, that just is in place for a number. And it even says here where p naught is the numerical value given in the null hypothesis. So the best way to do these, like I said, is go through an example. Okay. So this first example, it says a Gallup poll report on a national survey of 1,028 teenagers. Okay, it's a survey, so that's my sample size. Revealed that 72% of teens said they rarely or never argue with their friends. So this is a sample proportion, a p hat. So the p hat there is 0.72. It says Yvonne wonders whether this national result would be true in her large high school, so she surveys a random sample of 150 students at her school. So this referred to a larger survey. That's a larger survey. Okay. So this is a different type of N. All right. So that's the sample for her school. And it said 96 students in the sample said they seldom or never argue with their friends. So the p hat we got, or she got at her school, would be 96 over 150. Okay. And if you want to change that to a decimal, just in the calculator, do 96 divided by 150. And that's going to be 0.64. Okay. It says write the null and the alternative hypothesis. Well, so the null is the HO. All right. So before she took this survey, it says Yvonne wonders whether this national result would be true. So she's wondering if that's true from the national sample. So she's going to assume a row of 0.72. Remember, these always have to be parameters. Okay. So that's what she thinks it's the same. So if it's not the same, that means it wouldn't equal 0.72. Okay, but we always want to identify what the row represents, where row is the true proportion of students in Yvonne's school who rarely or never argue with their friends. So always identify what the parameter means. Okay, now it says calculate the test statistic. So since this is a proportions problem, it's going to be a z. It says we're going to take the p hat, which we found to be 0.64, minus the rho naughts. This is the rho naught value, all over the square root of the rho naught, the assumed center. So we're assuming the center is 0.72 times 1 minus 0.72 all over, okay, the sample size, her sample size, which was 150. Okay. So this one doesn't matter. That was from the national. Okay. Now this did matter because that's what she had to go on. Okay. So we're going to assume that turns into the rho. All right. So we can do this in one step on our calculator. Okay. We can just set up a fraction. 0.64 minus 0.72 all over big square root. Set up another fraction. 0.72 times 1 minus 0.72 over 150. Now before I hit enter, some common mistakes that students make, they'll put the 0.64 there. Okay, and you should not do that. It's the assumed center. It's what the rho actually is. Okay, so we're assuming rho is 0.72. All right, just hit enter there. So my test statistic would be negative 2.182. All right. So on our graph, we're assuming the center is at 0.72. And again, this is the sampling distribution of p hat. Okay. We got a p hat of 0.64, which is less than 0.72. And when we calculated the test statistic, this right here, okay, in that distribution it falls 2.182 standard errors or standard deviations below the assumed center. Okay, so the next part says find and interpret the p-value. So the p-value, okay, would be the area. Okay. Now, this is a two-tailed test. Okay, so after I find this area, I actually have to double it because there's a mirror on the other side. Okay, there's a mirror on the other side. So once I find this area, I got to double it. Okay. So how am I going to do that? Well, I'm going to store this. I'm just going to store it as z because it's a z test statistic. And then I know that this is a normal curve. And this is a normal curve. All right, so I'm going to go to my normal curve. I'm going to go normal CDF. All right, I'm going to go from negative infinity up to my z value. Okay, and in a standard normal curve, the mean is 0 and the standard deviation is 1. I can paste. Bingo. 0.0145. That's this area. But since it's a two-sided test, I got to count the other tail. So I got to multiply that times 2. At 0.029. So that is what the p-value would be. So it also tells me that, so we found it, but we have to interpret it. There is a 2.9% chance that we would observe a sample proportion as extreme or more extreme than that observed. Okay, so this is what we observed. So this extreme or more extreme than that observed if the true proportion were 0.72. Okay, so if the real proportion was 72% at this school, okay, there's only a 2.9% chance that we would get a p-hat that far away or more far, okay, on both sides. So on this side, that's a difference of 0.8, okay. And you can be more specific in this. You could say there's a 2.9% chance that we would observe you could say a p-hat okay, you could say a p-hat less than 0.64 or a p-hat greater than 0.80 if the true proportion were 0.72. Okay, so you can be more specific if you want. So there's only a 2.9% chance that would happen. Really small chance. So eventually we're going to say we're probably not believing that anymore. That's probably not the real or the true proportion, because that is such a low chance to happen. It's such a low chance that I would get a p-hat that far away from the center. I mean, you might just say, well, it's only 8%. Okay, well, it's not so much to do with that. It's how many standard deviations it is below. Okay, so hopefully that makes a little bit of sense. The more we do, the better you'll get this. So here's my process, which I kind of talked about, for doing any type of significance tests or confidence intervals for that matter. So I like to make a statement, okay, then do the condition check, then calculations, then decision, then conclusion. Now in confidence intervals, we got rid of the D, but with hypothesis tests, we need it. Okay, so it says state the name of the test you're conducting and state the hypothesis. Make sure that you tell the reader what your parameter signifies, i.e. rho is the true proportion of all students who argue with their friends at XYZ high school. And check your conditions, the random, independent, and normal condition. All right. Calculations. All right, that's what we did up here. We got this as a calculation. We found the p-value, which is a calculation. Okay. Make a decision. All right, this is if the p is low, reject the O. And then you make a conclusion. There's either sufficient statistical evidence at the blank level, or there's insufficient statistical evidence at the blank level. That's going to depend on the alpha level. All right. So let's just jump into it. Let's do a whole problem. All right. So it says example. The potato chip producer has just received a truckload of potatoes from its main supplier. Excuse me. If the producer determines that if more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load from the supplier. A supervisor selects a random sample of 500 potatoes from the truck. Okay, so your sample size is 500. And I'm just writing down the information from the problem. An inspector reveals that 47 of the potatoes have blemishes, so therefore the p hat is 47 out of 500. Okay. Or as a decimal, that's 0.094, 9.4%. Which doesn't look promising right now. Okay, because it says more than 8%. But remember, this is just a sample. All right, and it also tells us we want to do a significance test at the 0.10 level. What should the producer conclude? So we've got to go through our full process. So number one, I want to make some sort of statement. Okay. So my statement has to do with my hypotheses, so I need an HO and an HA. Okay. So my null hypothesis is that the true proportion is only 8%. Right. My alternative hypothesis, what I want evidence of, is that rho is greater than 8%. Because if I have evidence of this, then I'm going to send the truck back. But I need enough evidence. The question is this high enough? Is it far enough away from here to give me enough evidence? That's the whole purpose of these hypothesis tests. And then tell the reader what your parameter signifies, where rho is the true proportion of blemished potatoes in the entire truckload. Okay, so again, our process SC/CDC. You can think of whatever mnemonic device you want to. For some reason, I like to watch SportsCenter, so I remember SportsCenter, and then CDC is a government agency, Centers for Disease Control. I don't know why I remember it like that. That's just how I remember it. Just say to myself, SportsCenter, Center for Disease Control. You can probably think of something more clever than that, like stats can create decisions and conclusions or something like that, whatever you want to do. All right, so we got the statement done. All right, the next part, we should really do a condition check. Okay, conditions. Okay, so the first condition I'm going to check is the random condition. Okay, what we have right here tells us in the problem that's a random sample. All right, so I would just say random sample stated. Okay. Next check is an independence check. All right, so I want to make sure n is greater than 10 little n. So 10 times 500, hopefully you don't need your calculator for that. It's 5,000. So I need to make an assumption. Assume the entire truckload has more than 5,000 potatoes. And you just need to make an assumption and move on. All right. Now, the last one is the normal condition. With proportions, comes down to n times rho, okay, greater than or equal to 10, and n times 1 minus rho, greater than or equal to 10. All right. Now, the question is, what do you use? Do you use the 0.94? 0.094, or do you use the 0.08? You use the assumed center of that distribution, which is 0.08. So we're actually going to be using the P naught there. And now if this was a confidence interval, we have no idea what that is. So when it's a confidence interval, we use P hat. But in a test, since we're assuming some rho, this is what we use. Okay. So here that would be 500 times 0.08. And this one would be 500 times 0.92. Obviously this one's going to be much bigger. Okay, well, 8% of 100 is 8, so 8% of 500 would be 40. So 40 greater than 10, that checks out. All right, if that's 40, this would be 460, because both of these numbers are going to add up to 500. And if you don't believe me, just do it. 500 times 0.92. Then go 460. Awesome. All right. So we got the random met. We made an assumption. That's a pretty safe assumption. You can put a lot of potatoes on a truck. Okay, and the normal checked out. All right, so we got statement done. We got the conditions done. All right, so conditions done. Next, calculations. Okay, so what I like to do here, I like to name the test. You could also do it up here, but this is data coming from a single sample, and it's a proportion. So I would call this a one prop, and it's a test. So I put test at the end, and we're using the z-curve. The test statistic is a z test statistic. So this is called a one prop z-test, a one proportion z-test. Okay. So let's go ahead and get the test statistic. Now I can label it test statistic. Z equals, you can either put the formula, or since you've named it, that's good enough. It never hurts to write the formula though. So P hat minus rho naught all over rho naught minus 1, rho naught times 1 minus rho naught all over n. And that's the formula that we're going to use. That was the same on the previous page. Okay, our P hat was 0.094 minus the assumed center is 0.08 all over, be careful what you use here, use rho naught, 0.08, 1 minus 0.08, which again is 0.92, all over the sample size, which is 500. So we can do this in one step. Fraction, 0.092, or sorry, 0.094. Minus 0.08 square root, another fraction, 0.08, 1 minus 0.08 over 500. Do all that and you get 1.154. I'm just going to store it temporarily as Z. So what is this saying? This says that our P hat falls 1.15 standard deviations above the assumed center in our distribution. Okay, so if I made a curve of this, and it's a good idea to make a curve, we're assuming the rho is 0.08, that goes in the center. Okay. And our value of 0.094, okay, that has a z-score of 1.154. Okay, so that's the z-score, and that's the p-hat value. Okay. So how are we going to shade? We're going to look at our alternative hypothesis. It says greater than, so we're going to shade greater than. So the next thing I want to do is I want to find the p-value. Remember, that's a probability. So in other words, this is going to equal the probability that my p-hat is greater than 0.094, okay, which is also going to be the same thing as the probability that the z-value is greater than 1.154. Now I already have that z-value there. In a standard normal curve, now we can go to our normal curve, our normal CDF. We can say the lower starts at z, it goes up to infinity, and here's the standard, on the standard normal curve, the mean is 0, and the standard deviation is 1. All right, we can paste 0.124. So the p-value is 0.124. All right, so the interpretation of that, if this really is the true proportion of blemished potatoes, there's a 12.4% chance we would get a sample that was 0.094 or above, a sample proportion that was 0.094 or above. Okay? Still within reason to believe that that could happen. All right. So that's the end of the calculations. All right. Now I need to make a decision. So step 4 is the decision process. Okay. Your decision is going to be based on the p-value and the alpha level. Okay. And sometimes it's a good idea to put the alpha level up here, even though it's not a calculation. It helps look at these. So in our case, the p-value happens to be greater, this number is greater than the alpha. It's greater than the significance level because 0.124 is greater than 0.010. So if the p-value is greater than the alpha, our decision is to fail to reject the null hypothesis. All right, only if the p is low, reject the hoe. All right, this is not lower than that. The only time you reject is if this is lower than that. So we made a decision and we linked it to the p-value. You get points for doing that. Okay, one step left, and that is the conclusion. All right, so when we fail to reject, we start the conclusion this way. There is insufficient statistical evidence. We don't have enough. This is not far enough away from that to believe that that's not true. There's insufficient statistical evidence to show that the true proportion of blemished potatoes is greater than 8%. So I'm not believing that. I cannot accept this. Or I have to stay there. I have to stay with this thought. Okay. That's not low enough to believe that it couldn't just happen by chance. It needs to be much, much lower. It would have to be below 0.10 for me to believe it, based on this significance level. That's a high significance level too. All right, the threshold's not that high to beat. Okay, so there's insufficient statistical evidence to show that the true proportion of blemished potatoes is greater than 8%. So we don't believe this. Okay. Now, there is a way to do this in your calculator. All right. Since this came from one sample and was a proportion, one prop z test, if I go under my test here, if I go stat, go over to test, okay, go down to number 5, where it says one prop z test. All right, it's going to say, okay, what's the null hypothesis? Well, it's 0.08. Okay. How many blemished? X is the number of successes or blemished potatoes we got. We got 47. Okay. That comes from this data up here. Then it's asking me what the n is. What's the sample size? 500. Okay. And then it's asking me, well, what kind of test is this? Is it a right tail, a left tail, or a two tail? Okay. Well, in our alternative hypothesis, we have a greater than. So I would select the greater than. Then you can calculate it or you can draw it. Okay, let's just calculate. So what do you notice here? It gives me the z value or the test statistic 1.154. That's what we got right there, 1.154. Okay, it gave me the p value 0.124. That's just the p with nothing on it. Okay, 0.124, that's what we got as the p value. And just as a summary, it tells you what the p hat was, 0.094. We said 0.094. Okay, now if I did this same test, okay, let me just kind of do it again here. Make sure you have all your plots turned off and all your functions turned off. But if I go and do that again, okay, if you draw it instead of calculate it, okay, it'll put a normal curve on there and it'll do the shading for you, kind of like I did in this picture. Okay. So and then it'll tell you also on your graph what the test statistic is and what the p-value is. Okay, now in the past, they did not make you show both of these things. If you named the test, or if you wrote the formula and figured it out by hand, they didn't make you do both for the points. They said do one or the other. If you did both and you made a mistake, they would count off. Okay, so I would rather you do it by hand and just use the calculator as a check for yourself. Okay, but technically, if you put the proper z value, if you just wrote it down and named the test and put the proper p-value, you would technically get full credit if they grade it the same way as they have in the past. Okay, but this is a full, no doubt I'm losing any points on this, no matter how they decide to grade it. Okay, I've shown everything. Okay, so we got exactly the same answers as we did on the calculator. Okay, let's do another one. All right. So it says, this next example, according to the Centers for Disease Control and Prevention, CDC website, 50% of high school students have never smoked a cigarette. Taylor wonders whether this national result holds true in his large urban high school. For his AP Stats class project, Taylor surveys a simple random sample of 150 students from the school. He gets responses from all 150 students, and 90 say that they have never smoked a cigarette. What should Taylor conclude? Give appropriate evidence to support your answer. Okay. So let's go through our process. Step 1 is going to be our statement. Again, if we have to do Sports Center, Center for Disease Control, that's how I remember what to do. Okay. Statement, let's make our hypotheses. HO and HA are null and our alternative. All right, so previous data suggests that the true proportion is 0.50. Okay, all Taylor's wondering, okay, He's wondering whether this national result holds true, if it's the same. So that's why that's the null hypothesis. So what would the alternative hypothesis be? That it's not the same. Okay. So that's going to be a two-tailed test. Again, let's tell the reader what the row represents, where row is the true proportion of all students in Taylor's High School who have never smoked a cigarette. All right, let's go on to step 2. Let's do our condition check. Conditions. So we need to check random. We have to check independent. We have to check normal. I'll write normal down in a second. But do we have a simple random sample? Yes. It says right there. SRS of 150 students stated in problem. Okay. Independent. N has to be greater than 10n. Okay. So n has to be greater than 10 times 150, which is 1500. Okay. Do we know if that's true? Is there at least 1500 students in his school? Well, it does say that it's large urban high school. So I would write something to the effect of problem states that Taylor is in a large high school. So we will assume at least 1,500 students attend. Okay. So we're basically covering ourselves by making that assumption so we can keep going in the problem. So we did random, we did independent. Last one, let's do the normal condition, which is n row is greater than or equal to 10, and n times 1 minus row is greater than or equal to 10. Okay. We're assuming row is 0.50, so we're going to use that row not data. All right, now our n is 150, our row not is 0.5. Okay, so 50% of 150, 75, and that's greater than 10. This would also be the same thing because 1 minus 0.5 is still 0.5, so that's the same thing. 75 is greater than 10. All right, so random, independent, normal, all check out. So I've done my statement, I've done my condition check. Everything's working good so far. Okay. And readers like this when you break the problem up like this because they can identify everything you've done. Step 3 is going to be our calculations. Our calculations. So I'm going to get some key calculations here. All right. Before we can find our test statistic z, we need to figure out what p hat is. And if you did that before, that's fine. You could have done it up here. P hat, 90 have never smoked out of 150. 90 out of 150 would be 0.60. Okay. Now, it didn't give us an alpha in the problem. So I'm just going to make an assumption before I go any further. Assume alpha equals 0.05. If they don't tell you what alpha is, that's a safe number to choose. All right, so p hat, I'm just going to write it again here. It's 0.60. My sample size was 150. This would be a one sample proportion z-test because the proportions always match up with z. Find the test statistic. Okay. Z would equal sample proportion minus assumed population proportion over the standard deviation of that. Okay. So we would do it that way. So I would have 0.60 minus 0.50 all over 0.50, 1 minus 0.50 over 150. Do this one step in the calculator, 0.60 minus 0.50, square root of a fraction, 0.50, 1 minus 0.50, all over 150. 2.449. So my sample proportion fell almost 2.5 standard deviations above where we think the center is going to be. That's kind of far. So on our sampling distribution, all right, our sampling distribution, we assumed 0.50 was the center. Our actual p-hat was 0.60, so those p-hats. So we think about it in terms of z-scores. Center is a z-score of 0, and we just said that this was 2.449. So the next thing we have to do is we have to find the p-value. But remember, this is a two-sided test because of that, because of the not equal to. So not only do we have to find, after I find that area, I have got to double it because it could also fall on that side. So I basically, let's go ahead, let's store this as our z. Now let's find this area to the right using a standard normal curve. I'm going to go normal CDF. I'm going to go from z to infinity. 0 and 1 here because that's the standard normal curve. Paste. Hit enter. So that would be this area, but I have to double it. So I need to do 2 times that number, 0.00715. I'm going to take that and multiply it times 2, 0.0143. So that's the p-value. Okay, that's the test statistic. That's what they want to see under your calculations. Okay. Now, we have to make, so we've done calculations. Now we have to make a decision. So step 4 is going to be my decision. All right. So I got a p-value of this. So my p-value is less than the alpha that I assumed. And just for clarity here, I'm going to give my p-value back to the reader. Okay. I'm going to show what I assumed for an alpha. All right. So my p is lower than my alpha. When the p is low, reject the O. So my decision is going to be to reject the O. Okay. So that's it for decision. The decision is really quick. So let's talk about what this actually means again. So assuming that the school really has a true proportion of 50% that have never smoked a cigarette, there would only be a 1.43% chance that we would observe a sample of above 0.60 or below 0.40. Okay, these would be equidistant if it's a two-tail test. And that's what it means. Really small chance that that would happen. Because this is such a low probability of happening, we don't believe this anymore. We don't believe we would get a p-hat this far out. It's not likely enough to happen. So we have evidence against this in favor of this. That's where our conclusion comes in. And here's how I would write it. There is sufficient statistical evidence at the alpha equals 0.05 level to conclude that the true proportion of students at Taylor School, true proportion of students at Taylor School who have never smoked a cigarette what are we going to conclude? We're going to conclude in favor of the alternative. So I can say differs from 50%. That's all the test allows me to do. We don't know what the true proportion is, but I'm pretty confident that it's not 50%. Okay, because the probability of that being true is just not there. Okay, it's just not there. The probability of getting a p-hat that extreme, so small. So I don't believe that this is the true mean anymore, or the true center of that sampling distribution. Again, this is a sampling distribution. So that's my conclusion. So that's going to wrap it up for this section. Okay, just go through the process every time. I know it's tedious. Okay, let's just double check this one real quick. Let's make sure we got the right answers. All right, so again, stat tests, one prop z test number 5. Okay, it's asking me for what my p-naught, assumed p-naught was. It was 0.50. 90 students at the school never smoked out of the 150. Okay, it's a two-tail test. It's a not equal to. It's part of the alternative hypothesis. I calculate z 2.449, 2.449. P-value here 0.0143, 0.0143. It's good to have the calculator, because if you just said that was 0.007, you would forgot to double it and be like, why is my answer not matching? Use a calculator to check yourself. A p-hat of 0.6, we got the same thing, 0.6, when we did 90 divided by 150. And so it's a way to check it. Okay. Or if you did this with a graph, same data, but if you draw instead. Okay, it's hard to see the shading, but there's actually shading on both sides. Okay, why is it hard to see? Because the p-value is so low, the z-value is so high, because it's almost 2.5 standard deviations above. So the shading starts about 2.5. These tick marks each represent one z-score, a z-score of 1. So 1, 2, 3, -1, -2, -3, 0. Same thing as on our graph. That corresponds with a z-score of 0, and ours was 2.44. Okay. So it matches exactly. Now what we're going to do next is we're going to do hypothesis tests, but we're going to do them for means instead of proportions. Okay, same process. So, until next time.